Hello chemists, this is Ms. Placino and you're watching lesson 7.2 on types of solids. In today's lesson we're going to review the different types of solids and kind of just what their general properties are. So some goals for today's lesson, we'll be able to classify solids as either being amorphous, ionic, network covalent, metallic, or molecular, really just by looking at their chemical formula. We're going to be able to recall the general properties of each type of solid. And we're going to be able to predict the electrical conductivity of a solution. All right, let's go ahead and get started. I'm going to start off with two broad categories of types of solids. We have something called crystalline and another group called amorphous. And if you look closely at these two structures, one of quartz and the other for glass, you should see that the elements present are the same. We get silicon and oxygen in both cases. And they're the same ratio. We've got SiO2 in both cases, so a 1:2 ratio of silicon to oxygen atoms. What really jumps out at you as the major difference between these two solids? I'm hopeful that it's organization. Quartz is highly organized, whereas glass is kind of a jumbled mess for the most part. Crystalline solids are well organized. Very high degree of organization. Due to this high degree of organization, they have a definite melting point. If you go to melt a crystalline solid, it's going to, the entire sample melt at the same temperature. Amorphous solids, that's not the case. With amorphous, you have very little to no organization. Occasionally you might get like some chunk of it kind of organized, but most of it is really just a mess. And as a result, you see a range of melting points. If you think back to the first lab that we did where you were working with the glass tubes and melting them to make different pieces of glassware, there wasn't one temperature where suddenly like your entire piece of glass melted. Because it's amorphous, it's going to melt at a range of temperatures. So there's going to be like a stretch of temperatures where you'll start to go from a solid to a more pliable liquid. Again, that has to do with the fact that this has virtually no organization. So we're really going to focus in on today's lesson, taking the crystalline solid group and kind of breaking it down into smaller subgroups with different properties. And again, our goal is really going to be able to take the formula of the solid and predict what type of solid it is, if it's amorphous or crystalline, and if it is crystalline, what type of crystalline solid. So let's spend a little bit more time reviewing the crystalline solids. Here's a picture you've definitely seen before in my lessons. This is sodium chloride. What type of bond is going to exist between the sodium and the chloride ions? Hopefully you're thinking ionic. This is an ionic solid. Ionic solids tend to be very large networks of cations and anions. So you can kind of think of like this big three-dimensional cube of just repeating cations and anions. Like other crystalline solids, they tend to be highly organized. We'll see alternating cations and anions trying to minimize the repulsive forces between like charges and maximize the attraction between unlike. Ionic solids all have high melting points. And I know that's kind of a general term. When we say high melting point, basically we mean you can't melt it at home in your kitchen, like on the stove. If you're like an acetylene torch or something like that, sure, you can melt an ionic solid, but under like a simple Bunsen burner flame, or if you are cooking with gas at home, unlikely that you're going to melt most ionic solids. So we'll say that they have high melting points. One thing that's really cool about ionic solid is its ability to conduct electricity. When I take an ionic solid and I dissolve it in water, we'll talk more about this later, but the attractive forces between the oppositely charged ions will be broken, and that's going to leave the ions free to float around in solution. These free-floating ions are able to conduct electricity. So this will happen when we have an aqueous solution, so dissolved in water, and if you're able to liquefy the salts. Sometimes you might hear this called a molten salt. Definitely a little bit more dangerous to work with and difficult to melt it into a liquid. Aqueous is far easier. You're going to see conductivity in both cases. Again, we'll dive more into that a little bit later. All right, up next we've got network covalent solids. What type of bond must be present between the atoms in a network covalent solid? Yeah, covalent. These are going to be large networks of covalently bonded atoms. These are fairly rare. We don't usually see these big, expansive networks of atoms that are bonded together covalently. Really common for ionics, rather rare for covalents. They are highly organized. They tend to look more like an ionic than a covalent. Again, we're going to see that high melting point. High meaning it's going to be difficult or impossible to melt over like a Bunsen burner flame. And typically they tend not to be too conductive of electricity in their, well, really in any phase for that matter, but we'll focus on the solid. There are a couple of network covalents that you're just going to have to memorize. You're already familiar with two of them. Here they are. We've got diamond and graphite. Another good example, it's not on here, but it showed up in those first pictures, like quartz. It's a good example of a network covalent solid. In the case of both graphite and diamond, they're both forms of carbon. That's 100% graphite or just a very pure diamond. It consists exclusively of carbon atoms bonded to one another. Now, of course, they've got really different properties. If you were to get down into a molecular level and see what was happening in graphite, you kind of have these like sheets of carbon atoms that are all bonded together, kind of like in that sort of form, that trigonal planar geometry, a double bond and two single bonds coming off of each carbon. If you're writing with a pencil right now and you go to press down and put something on paper, you're breaking these attractive forces between the layers and you're leaving just a trail of carbon atoms behind you. Kind of cool. If you were to look at diamond on the molecular level, you see more of a like tetrahedral type geometry. Each carbon being bonded to four other carbons. Very different structures. We're going to see a greater density with diamond, a different degree of organization. So we end up with two very different sets of properties despite having really the same chemical formula. There's a whole bunch of carbon. These are sometimes called allotropes of each other. And you might want to jot that down somewhere off in the margin. So you've got like two different forms of the same element. Another good example is O2 and O3, oxygen gas and ozone. So just kind of some fun facts about these. There's no way that you could just really figure out, I should say, that graphite is a network covalent. It's one you're going to have to commit to memory. So know these two. And this is another good one to remember. All right, I got beryllium and barium. What type of elements are beryllium and barium? Let's see, I find them on the left-hand side of the periodic table. They look lustrous, solid. These look like metals. Our third type of crystalline solid is a metallic solid. Metallic solids get their properties through this sea of shared mobile electrons. Basically, electron communism. If you think about your history and global studies classes, when we think about communism, we think about all of the resources being shared equally. The resource in this case are the electrons. So you kind of have like a clump of positively charged ions, like metallic cations basically, and then this sea of moving shared mobile electrons. That is going to lead to like the conductivity that we see of metallic solids. Here's another picture of it. We've got our metal cations, and then we've got these delocalized, which really just means free to move electrons kind of flowing all through this tightly packed group of metal cations. Metals are very conductive of electricity. When you apply a current, you can get all of those mobile electrons moving in the same direction, hence electricity. Very high melting points for most metals. Again, you are not going to be able to melt it using a Bunsen burner. Sure, there are some kind of neat exceptions in the periodic table, but for the most part, we tend to see high melting points. And finally, if there's a metallic element, something like beryllium, barium, then let's pick one. Most of the elements on the periodic table are metallic. They count as a metallic solid. It also includes alloys. We talked about alloys It's been a while. Do you remember? It's a mixture of solids. For example, something like bronze. It's not an element, it's definitely a metal, but it is an alloy of different metals. And now that I put it on there, I can't, and is that copper and zinc maybe? I want to say that's copper and zinc. I could be mistaken about that. But we form an alloy by taking two metals, melting them down, and then kind of mixing them together to homogenize it, letting it cool back into a solid. That's an alloy. They also will count as metallic solids. All right. Last but not least of our crystalline solids are molecular solids. So we've talked about ionic bonding, very specific covalent bonding, and metallic bonding. Molecular solids really are all of the other covalents. So these are going to be covalently bonded molecules, and they're going to be held together by intermolecular forces. These are the forces we talked about in the previous lesson. Things like the dipole-dipole force for our polar molecules, H-bonds, very specific type of dipole-dipole force, and London dispersion forces. If these are totally foreign to you, you might want to go back to lesson 7.1. Molecular solids have low melting points. You can melt these at home, or you can melt them using a Bunsen burner. You see it happen all the time with water. We know we've got hydrogen bonds holding the water molecules in a fixed location in ice. And then, if you leave an ice cube out at room temperature, that's going to be warm enough to melt the solid. In other words, just kind of compromise those really rigid bonds and allow the molecules to move more. Molecular solids do not conduct electricity. And you might be thinking, well, wait a second, I know that I'm not supposed to take a bath and blow dry my hair simultaneously, so water does conduct electricity. Careful. Water, like tap water, is not the same as pure H2O. There are other compounds, some that are naturally, some that have been added, but it's not just liquid water. So what I'd like to do is take a minute and look at a couple of practice problems. So I will meet you there in just a moment. All right, here we are in the practice problems. This is kind of what I expect you to be able to do. We've got different solids listed, and you are going to try to identify them as either being ionic, network, molecular, metallic, or amorphous. And I would like you to check out, we'll do this last column, 11 through 15. So pause the video. Try out those 5, then get it started back up again to check your answers. All right, let's go over these. So number 11, we start with sulfur. Sulfur is a non-metal, so it probably won't bond ionically. You've seen sulfur before. It's kind of like a powdery yellow substance. Unlikely it's a network. Probably not metallic. Yeah, this is a molecular solid. And we'll kind of review how to identify them at the end. Okay, plastic. This could be a tough one. Definitely not ionic or metallic. Plastics consist of molecules called polymers, which are these really big, long, repeating chains, and you can kind of get crisscrossed over each other and all mixed together. Through that description, you might be able to conclude that these tend to be amorphous. Now, plastic is a really vague term. There are all different sorts of plastic. You've got your really flexible plastics, like a plastic bag. Then you've got more kind of hard plastics, like a phone case, for example. But we'll treat plastics as though they are amorphous. Brass. Brass looks like a metal, but it's not on the periodic table. Must be an alloy. That'll make it a metallic solid. Graphite. It's one of the handful of network covalents you kind of just have to memorize. And last in the group we have CO2. Wait, that's a gas. Well, we're still thinking about it as a solid, and we know that we can have dry ice, which is frozen solid CO2. Let's see, that's covalently bonded together. Yeah, that must be a molecular solid. So just to kind of break some stuff down, ionics. Look for an ionic bond. It's got an ionic bond. It's going to be an ionic solid. With our networks, we're looking for really graphite, diamond, quartz. Are there others out there? Sure. Do you have to worry about them? No. Molecular. You can look for covalently bonded small molecules. CO2 counts as a small molecule, for example. Sugar, glucose, C6H12O6. Consider that a small molecule. Metallic, it's going to be a metal element or an alloy. And amorphous, I probably won't give you too many of these to look at. Things like plastic and glass are good examples, but these are just going to be messy on a molecular level. I would definitely suggest doing some more practice with these concepts. All right, let's get back to the notes and finish stuff up. All right, what I'd like to finish with is the idea of electrolytes and the ability of a solution to conduct electricity. So in class we'll be doing a demonstration. We've got 3 different solutions. One contains sodium chloride. The other is just pure water. That's an L. It's in script to hopefully make it a little bit easier. And C contains an aqueous solution of sugar, sucrose, just like a table sugar like you probably have at home. We're going to take those substances, dissolve them in water, except for water, of course it's just a pure substance. What I'd like you to do is kind of visualize what would be happening on the molecular level. What would we see if we were able to shrink ourselves down small enough? And what we have here is a incomplete circuit. So we've got a source of power, we've got a light bulb, we've got these 2 electrodes in the solution. And if the solution is conductive, the light bulb will glow. If it is not, the light bulb will not glow. So what I'd like you to do is try to sketch what you think you'd see in each of these and predict whether or not that sample will be able to conduct electricity. And if you can, briefly explain why. Have you made your predictions? I hope so. Now let's kind of dive in and look at this a little bit more closely. So you've seen this video before, but it is worth playing again to remind you what happens when you take something like sodium chloride and you dissolve it in water. We've got the crystal lattice getting pulled apart by the water molecules. We know that water is polar. This ionic compound is composed of ions, so the negative side of the water molecule can grab the sodium cation. The positive side of the water molecule can grab the chloride anion and pull them off into solution. So we're going to have these ions free floating and free moving in the solution. We don't see that with every single substance that gets dissolved. It needs to be ionic. So if you predicted that the sodium chloride light bulb, or the solution with the sodium chloride could get the light bulb to glow, you are correct. On the molecular level, we should see water molecules present, and we should also see ions. There's like your chloride ion, there's your sodium ion. And they're just moving around in the solution. Since this solution is able to conduct electricity, and we know that because the light bulb is glowing, we would say that NaCl, sodium chloride, is an electrolyte, or that aqueous sodium chloride is an electrolytic solution. So when we say electrolyte, we're just talking about a solid that will form an aqueous solution that is capable of conducting electricity. In order for this to happen, you need mobile ions in solution. If the ions aren't free to move, electricity will not be conducted. If I took those electrodes and I just stuck them in solid sodium chloride, the ions can't move, so electricity will not be conducted. Often, electrolytes tend to be substances that are ionically bonded. In other words, an ionic solid. My guess is that you've heard electrolyte before. Maybe in bio class, maybe well before that. Especially if you're physically active, there might be something that you drink to try to replenish your electrolytes. Yeah, sports drinks like Gatorade have electrolytes in them. If you are working out and if you ever tasted your own sweat, I'm sure you have, and I don't mean like you notice sweat on your arm, you stop what you're doing and you lick it, but like you're working out, you're sweaty, you lick your lips. What do you taste? It is salty. So Gatorade is making a fortune by selling you very dilute salt water that they've also crammed a bunch of sugar in. If you've got a solution of Gatorade, you should be able to conduct electricity with it. Now, you know, hopefully from experience, you've had Gatorade before. It isn't like crazy salty. So maybe you wouldn't get this light bulb to glow super bright because there are not a lot of ions in solution. You would only see like a dim glow. But in theory, it should still conduct electricity. You know that liquid water is not going to be conductive. Let's take a look at a solution of sucrose, so sugar water. Sugar water gives me energy, maybe it'll give light bulb energy. No, not the case. We can see on the molecular level, we've got our water molecules, and then these big clusters of molecules, those are the sucrose. You can see they have not broken apart into ions. Sucrose is an example of a non-electrolyte, which, as you might conclude, is a solid that does not form an aqueous solution capable of conducting electricity. Carbon, hydrogen, and oxygen are covalently bonded together. So when they dissolve in water, they are not going to break apart. Water can separate ionic attractions, not covalent bonds. So you will see no ions in solution. Again, this is often going to be observed when you have a covalently bonded molecule, a molecular solid. We will talk about weak electrolytes versus strong electrolytes and how this is impacted with things like acids and bases, but that's still a couple units away. All right. I think that kind of wraps it up for today. Thank you for tuning in, chemists, and I will see you again soon.